Hi folks, we're going to take a look at the solution to number 12 from page 257. So what we have is we have a sheet of metal, so kind of like this piece of paper that we're folding over to create that trapezoidal shape to create an irrigation channel. Okay, so the water is going to be flowing through here, and we want to bend the metal over so that we maximize the area of this cross section, which as we see is just a trapezoid. Okay, now it's an isosceles trapezoid because they tell us that these angles are the same, so it means the angles inside the trapezoid are also the same, parallel line principle. Okay, so what we have to do is we have to, first of all, come up with an equation to represent what it is that we're trying to maximize. So what we're trying to maximize is the area of this trapezoid, and the area of a trapezoid is given by, well, if this bottom part is A and this top length is B, and then H represents the height of the trapezoid. Well, the area of a trapezoid is given by A plus B times H divided by 2. Okay, so an old, one of your old grade 9 formulas. Okay, so what we want to do though is we're measuring this with respect to theta. Okay, so we want to know what theta we're going to choose to maximize that area. So that means that all these variables, so first of all, we have too many variables. We need to bring this down to just one variable. But essentially what they're telling us is you want to write this in terms of theta. Okay, so we're going to have to write A, B, and H somehow in terms of theta. Now, A actually is not a problem because that's just equal to 1. Okay, we have this side of the trapezoid. So if we take a look at B, okay, this side here, well, you notice if I just kind of draw these heights all the way up, well, that's also equal to 1. So we just have to determine the lengths of these two sides. Okay, so let's call that x, and that'll also be x. So essentially B is just going to be 1 plus 2x. Okay, and then we have the height. But we want to do all this with respect to this angle theta, and we see that we've created a right angle triangle. Okay, so here we want to relate side lengths to angles, so here we should be thinking primary trig ratio. So that'll also be equal to x. So here we have sine of theta. If I start working with the h, is just h over the hypotenuse, which is 1. So we have the height is just equal to sine theta. And then similarly, we do the same thing for x here. We're going to see that x is just going to be equal to cos theta, because cos theta is x over the hypotenuse of 1. Okay, so now we have all the information we need in order to write area in terms of this variable theta. Okay, so A is just equal to 1 plus B, which we said was going to be 2x plus 1, okay, or 2 cos theta plus 1, okay, times the height, which we found was just sine theta, all over 2. Okay, so what we've done is we've managed to determine exactly what we needed. So let's try to determine the constraints on the variable. Okay, so obviously we don't want the angle to be more than pi over 2 radians. Okay, it doesn't make sense that it's folded inwards. Okay, and I guess at the very least you would need it to be just slightly greater than 0. You can't have theta to be equal to 0 because then you just have a flat sheet of metal, and so you don't have anything that's holding up the water. So here I guess we can say that theta is going to be greater than 0 and less than or equal to pi over 2. Okay. So let's, I would say it's worth simplifying this before we go ahead and take the derivative. So here we have, this becomes 2 plus 2 cos theta times sine theta over 2. And I'm going to factor out the 2 here, okay, because some nice stuff will then happen. The 2's cancel out, and I'm just left with 1 plus cos theta times sine theta. Now, I could take the derivative of this expression here, but I think it's actually going to be easier to take the derivative by multiplying this out. Okay, so I'm going to write this as so sine theta times 1, so sine theta plus sine theta times cos theta. Okay, and this is what I'm going to work with now to determine my optimal value. So start by taking the derivative here. So derivative sine is just cos. Okay, plus, well, here I've got a product, so I'm going to have to use the product rule. Okay, so here derivative sine is cosine, so cos theta times the second function cos theta plus my first function sine theta times the derivative of my second function negative sine theta. And so what we have in the end is cos theta, okay, plus cos squared theta minus sine squared theta. And we want to figure out when this is equal to 0 since we're looking for our critical points. Okay, now this is where things get a little dicey because I'm not quite seeing how I'd be able to solve this. Okay, I mean we could factor out a cos theta here, but that really doesn't look like it's going to help us. Okay, so this is where now we have to go back and remember all that work we did with trig identities. This is where we're going to see the importance. And I know that, or I hopefully recognize that cos squared theta minus sine squared theta, okay, should look familiar. Okay, that's the same thing as cos 2 theta. Okay, and I know that cos 2 theta has two other versions of it. Okay, now since I have a cos theta here, what I'm going to do is I'm going to rewrite this as the version that only has cosines in it. Okay, so cos 2 theta can also be written as 2 cos squared theta minus 1. Okay, and now I've got something that seems a little more workable because, again, hopefully now, again, from advanced functions that we notice that this is a quadratic trigonometric equation. Okay, so let's just, rearrange things to make it a little easier to work with. Okay, and the question is can I factor this? And it looks like I can. Okay, if I take 2 cos theta and a cos theta there, okay, I needed to add up to cos theta, so positive cos theta. So I'll put the plus 1 here and the minus 1 there. Let's give a quick check. 2 cos squared theta, 2 cos theta minus cos theta, there's our middle term, and negative 1 times 1, there's our last term. Okay, and now we can solve this. So here we have cos theta is equal to a half, or cos theta is equal to negative 1. Okay, now keep in mind, okay, and this is why it's really important to always come up with the constraint on your variable. Keep in mind that we're only working between 0 and pi over 2. Okay, so I'm only working in the first quadrant. Okay, now cosine theta is never equal to negative 1 in the first quadrant. Okay, because cosine is equal to negative 1 out there at theta equals pi. So that one's gone. Excuse me. Okay, so I just need to determine where cos theta is equal to 1 over 2. So since my numerator is 1, that's my x value. 1, 2, root 3. Okay, so theta is going to be equal to pi over 3. Okay, but we have to check that this indeed gives us a maximum, because that's what we're looking for. So let's test that. So we're only interested in 0 to pi over 2. So let's check pi over 3. Okay. And here, I can use any version of my derivative. I'll use this version here. And you know what? I'm not even going to bother putting in nice values. I'm just going to take my calculator. Okay. So here, let's pi over 3 is a little, 3.14 divided by 3, so it's a little less than 1, so I'll put 0.5. Okay, so let's see what we have here. Okay, so here we have cos, and make sure calculator's in radians, so we have cos of 0.5, okay, plus 2 times cos of 0.5 all squared, and then minus 1. Okay, and we get a positive number, so that's a good start. And now here, pi over 2 is about 1.5, so let's take 1.4, okay, for the other side. Okay, so we have cos of 1.4 plus 2 times cos squared, so cos of 1.4 all squared, and then minus 1, and here we have a negative value. Okay, And if we look in this interval, we see that it's always increasing, and then afterwards it's always decreasing. So that's indeed an absolute maximum in this interval. Okay, so now I'm going to go back to my question and see exactly what they're asking me for, and it says what angle will maximize the cross-sectional area. So my answer here is going to be an angle of pi over 3 radians. Okay, and there we have it. So just a quick recap. Okay, number one is to realize that we're maximizing a particular shape, in this case here a trapezoid, so get that formula. Number two is to realize that we're interested in talking about the angle, so that's why we had to rewrite all these three variables using the variable in question, which in this case here was theta. And another thing to bring up is the fact that we had to use some old tricks from trigonometry, namely using our trig identities for cos 2 theta, and then using our methods for solving quadratic trigonometric equations. Okay, that's it for this one.